Roster. Loading. Options.
Complex pedantic theorem.
Standard Deviants present The Many-Sided World of Geometry, Part 1.
Hey, I'm Tim Gore, and welcome to the Many-Sided World of Geometry, Part 1. Over the course of this information-packed program, we're going to help you learn all about lines, rays, angles, theorems, postulates, proofs, triangles, and a bunch of other geometric stuff. Then, along with some cookies, toothpaste, a little cash, and a note from home, we'll fit it all into a polygonal care package and ship it off to your brain.
Now, we know that geometry can be a really rough ride at times. The Standard Deviants have scoured the nation for all the basic geometry material you need to know, and then hired some great geometry instructors to help us. You can count on us to simplify this stuff and make it easy to learn, easy to remember, and just a little bit enjoyable. That's our job.
With this DVD program, you're in control of your learning experience as never before. Check this out.
You'll always start off from a main menu. Anytime you want to start over, just select Menu on your keypad. That'll bring you back to the main menu. From there, you've got lots of choices. You can view the program straight through, select which lesson you want to view, take a quick review, tune into some helpful info, take the Proof-O-Rama, a proof-based final exam, or learn more about Cerebellum, the creators of this DVD program. You can also hit Previous and Next at any time in the program to jump between major sections without returning to the main menu. What more could you ask for?
Now that we've got that down, let's get right into the geometry.
Part 1. Geometry Basics.
Geometry, like most forms of math, dates back to ancient times. A lot of what we study in geometry today was discovered and written down by ancient Greeks, guys like Pythagoras and Euclid. Actually, the type of geometry that is studied most in schools today is called Euclidean geometry, after old Euclid himself.
Euclid based his theories about geometry on one key idea about parallel lines, which we'll learn later in this program. For now, just realize that geometry has to do with shapes, the parts that make them up, and their relationship to each other.
So geometry is a different kind of math than algebra, and it requires a different kind of thinking. It's not so numbers-based, it's more visual. To get you geared up for it, we're going to spend some time thinking about geometry.
Section A, Thinking about Geometry.
In geometry, we use two kinds of reasoning: inductive reasoning and deductive reasoning. We use inductive reasoning when we recognize patterns and make observations. Then, as we examine why these observations happen, we use deductive reasoning.
Here's an example of inductive reasoning. Let's say that your friend picked you up in a red sports car this morning. And over the past few months, you've observed this same pattern. every morning your friend picks you up in a red sports car. So you guess that tomorrow morning, not only will your friend pick you up, but he'll be driving a red sports car and not, say, an elephant or a van. We expect this because inductive reasoning leads us to expect the observed pattern, your friend in the red sports car, will continue.
In geometry, we use inductive reasoning when we recognize details about different shapes and the parts that make them up. As we encounter different shapes over and over again, we'll see certain patterns begin to emerge. Recognizing those patterns is what inductive reasoning is all about.
Deductive reasoning is used when we examine the reasons why something happens. Deductive reasoning has been used by everyone, from Sherlock Holmes to Batman. Don't worry, it's not just for crime fighters. We all use deductive reasoning when we check out our inductive observations. We'll use logic and previously accepted or proven facts, because we can't accept an observation as true until it's been proven. We'll see deductive reasoning in action later on when we solve proofs.
While inductive reasoning leads us to anticipate that your friend will pick you up in a red sports car, we could only prove that he'll pick you up with deductive reasoning. We'd have to know that he left his house on time, he remembered where he'd parked his car started, he remembered how to get to your house, and you were waiting at the door, plus a bunch of other things. The point is, with deductive reasoning, we examine what leads up to the observation.
Now that we have an idea of how to approach thinking about geometry, we can begin speaking the language of geometry.
Section B, points, lines, planes, and space.
What are space, planes, and what?
Points, lines, planes, and space are the building blocks of geometry. Why? Well, geometry is a visual math. We're going to be seeing a lot of different shapes and looking at how they're put together. Then we'll look at the relationships between the parts of one shape and another. It's really kind of cool. It's not all equation-y like algebra. And it doesn't include gerunds and Ethan Frome like English. So let's get started with the basics.
In geometry, it doesn't get much more basic than a point. A point is represented by a dot. It has no length, width, or self-esteem. It's just a placeholder, really. We usually name a point with a capital letter, such as B, C, or X.
A line in geometry has no width, but its length extends infinitely in two directions. Usually, we name a line with a lowercase italic letter L, or by naming 2 points on the line and topping them with a 2-arrowed symbol. Collinear points are points which lie on one line, such as A, B, C, D, and S, T, U.
A ray is a lot like a line, except it begins at one point and extends infinitely in one direction from that point, like this single ray from the sun. As we see, ray AB begins at point A and goes through point B without ever ending or getting thirsty. We write ray AB as AB with a single arrowed line on top.
A segment is the part of a line or ray that is between 2 points. Here, segment TE begins at point T and ends at point E. We write segment TE as TE with a solid line above it.
In ray AB and segment TE, A, T, and E are the endpoints. So a ray has one endpoint and a segment has 2 endpoints. By the way, a line doesn't have any endpoints. It just goes on forever, like True Love and Seinfeld reruns.
Okay, that's a lot of different ways to talk about lines and stuff. Now that we know all that, let's talk about ways to split them up.
First, there's betweenness. We say that point R is between points T and E only if T, E, and R all lie on the same line, and together TR and RE equal TE. So let's say that the measure of segment TR equals 5 inches, and the measure of segment RE equals 3 inches. Then TE equals 8 inches. That's really just a complicated way of showing that R is between T and E.
A midpoint is the exact middle of a segment. Not a little to the right or a little to the left, the exact middle. O is the midpoint of segment TE. When a line, ray, segment, or plane, which we'll define in a minute, crosses a segment at its midpoint, it's said to bisect the segment. Not dissect, but bisect.
Let's note 2 things. 1, lines and rays cannot have midpoints because they're infinitely long. And because they're infinite, there can't be a middle. 2, when a segment is bisected, its halves are what we call congruent.
The terms congruent and equal are very important in geometry. We use them in similar but different ways. So now, let's distinguish between their usage.
Let's say that segment TE is 2 meters. It has a midpoint, O. So its two halves, segments TO and OE, have the same length, 1 meter. To put this in terms of geometry, we'll say that the lengths of segments TO and segment OE are equal. 1 meter equals 1 meter. However, the segments themselves, not their measurements, are congruent. Segment TO is congruent to segment OE. This symbol means congruent.
Congruence is very important in geometry. Not only can the measurements of segments be congruent, but so can the measurements of angles, triangles, and other polygons we'll talk about later.
We've covered all the basic line definitions that we'll need, so let's move on to planes and space. When I say planes and space, it's nothing like the space shuttle or some sort of star chariot. Oh no, we'll be talking about something different when we refer to planes and space.
Think of a flat surface like this tabletop and imagine extending it infinitely in all directions. This is a plane, which we'll label with a capital letter P. All the stuff we've talked about so far, points, lines, rays, and segments, all exist in a plane somewhere.
Remember collinear points? Well, now we have coplanar points. These are points that lie in the same plane. Points A, B, C, D, and E are all coplanar points in plane P.
Coplanar lines are, as you'd expect, lines that are on the same plane. Here's an example of two coplanar lines, line L and line M, that extend infinitely without crossing. These are parallel lines. This is how we write line L is parallel to line M.
If lines aren't parallel, they cross and are called intersecting lines. The one point at which they cross is called the point of intersection. There's no special notation for intersecting lines.
Now let's talk about space. Space is a set of all points in 3 dimensions. We experience space every day. It's all around us. We're in it right now. It's here, here, even here, possibly even over there.
Now, points, lines, rays, and planes all exist in space. Here are 2 lines in space that'll never intersect. Notice also that they're not parallel. We call these lines that never touch skew lines. Notice that lines in space which are not coplanar will never meet. So if lines meet, they must be in the same plane. Likewise, parallel lines are always coplanar.
So let's review our definitions. A point has no length or width. A ray begins at one point and extends infinitely in one direction. A line extends infinitely in both directions. A segment is the part of a line or ray between 2 points. A midpoint is the exact middle of a segment. When a line segment, ray, or plane crosses a segment at its midpoint, it's said to bisect the segment. A plane is a flat surface that extends infinitely in all directions. 2 lines on the same plane are called coplanar. 2 coplanar lines can either intersect or be parallel. And space is the set of all points in 3 dimensions. That's it.
Now that we have our basic definitions down, let's move up to the next level.
Section C, postulates and theorems.
The words postulate and theorem may be new terms to you, but don't worry, they're really simple to keep straight. A postulate is an assumption we'll accept without proof. On the other hand, a theorem is a statement we can prove with the help of the postulates and the definitions we talked about earlier, plus some basic things from algebra.
There's one more thing you need to know before we talk about postulates and theorems, and that's the word unique. If we say there's a unique line, or plane, or ray, or point, or segment, or anything, we don't mean that it's unusual or kind of quirky. We mean that it's the one and only line, or plane, or ray, or segment, or anything in existence that meets the given specifications. You'll see what we mean.
Okay, now it's time for the postulates. To get started in geometry, we need to accept some basic assumptions that we'll base the rest of our work on. These basic assumptions come in the form of postulates. Remember, postulates are assumptions that we accept without proof. Coming up are our first 6 postulates. Don't worry if they don't make a lot of sense to you now. You'll see how they work as we go along.
A line consists of at least 2 points.
Postulate.
A plane consists of at least 3 non-collinear points.
Postulate.
4 points not all in one plane are the minimum number of points needed to determine space?
Postulate.
There is one and only one line through any 2 points.
Postulate.
There are an infinite number of planes through any 2 points. But there is only one, that is, a unique plane through any 3 non-collinear points.
Postulate.
When 2 planes intersect, they intersect in a line, like the intersection of these 2 planes here.
Now that we have some postulates to draw upon, we can use them as we begin to explore theorems.
Now, what are theorems?
Theorems are statements we use in geometry that can be proven with postulates, definitions, and other properties we'll see later. All of the following theorems can be proved using the postulates we just gave you. Don't worry if they seem confusing now. You'll get the hang of it as we go along.
If 2 lines intersect, then they intersect at a unique point.
Theorem.
If 2 lines intersect, then there's a unique plane that contains them.
Theorem.
If a plane and a line not on that plane intersect, then their intersection is a single point.
Theorem.
Every segment has exactly 1 midpoint.
Theorem.
There's a unique plane containing a line and a point which is not on that line.
I've got you. So I've got a line over here and a point over here. So there's only one plane going through them both.
That's right, Tiger. Now, just as you think you're beginning to get this geometry stuff down, we've got to throw another curve at you. But don't get mad at us. Get mad at Euclid. Anyway, here's the deal. Each of these theorems can be stated in 4 different ways. To understand this, let's look at an example.
Let's take the statement, if I'm good, then I hold the monkey. This is called an if-then statement, just like our theorems are, if P, then Q. The if part, or P, is, if I am good. The then part, or Q, is, then I hold the monkey. If I am good, then I hold the monkey. This is the statement in statement form. If we reverse our statement, if Q, then P, we get, if I hold the monkey, then I'm good. This is called the converse. We can also negate our statement. If not P, then not Q. If I'm not good, then I won't hold the monkey. This is called the inverse. We can even reverse and negate our statement. If not Q, then not P. If I don't hold the monkey, then I'm not good. This is called the contrapositive. Now, let's see how all this applies to theorems.
Here are the 4 ways theorems can be stated in if-then statements. There's the statement, which is the form the theorems we just went over were given in. There's also the converse, the inverse, and the contrapositive. Let's take a look at the statement and the converse of one of the theorems we just went over.
Here's our statement in the good old if-then form. You know, if P, then Q. If 2 lines intersect, then they intersect at a unique point.
If we take our statement in if P then Q form and reverse it to if Q then P, this gives us the converse. The converse is, if 2 lines have a unique point in common, then they intersect.
So that's the statement and its converse. Later on, we'll prove theorems by proving, step by step, the statement and its converse. We won't go over the inverse and the contrapositive now, because if the statement is true, the contrapositive is also logically true. Likewise, if the converse is true, the inverse is also logically true. This all seems more confusing than it really is. Just know that there are 4 ways to state theorems, and also that when the statement and its converse are true, all 4 statements are true.
When all 4 of the if-then statements, the statement, the converse, the inverse, and the contrapositive are true, they're especially strong. We can unite their forces to create a big superstatement.
This superstatement is known as the biconditional statement. A biconditional statement has the form P if and only if Q. So the biconditional of if 2 lines intersect, then they intersect at a unique point is 2 lines intersect if and only if they intersect at a unique point.
And when we say it and prove it, it means that all 4 variations of the theorem are true. As we prove theorems in the if and only if form, the biconditional form, we'll prove the statement and its converse. We won't need to prove the contrapositive and the inverse because they'll be true if the statement and converse are true.
All right, we'll get to more if and only if statements when we prove theorems later. Before we move on, let's make sure we've got the basics.
A postulate is a fundamental assumption that can't be proven but we accept as true. A theorem is a statement that can be proven with postulates, definitions, and other information we'll talk about later. There are 4 different if-then statements: the statement, the converse, the inverse, and the contrapositive. We can form an if and only if statement when all of these are true. We'll prove the statement and the converse as we show the validity of theorems.
Quiz 1.
Part 2, Angles. Section A, Angles defined.
Okay, an angle is 2 rays that share the same endpoint. Let's take a look.
At point A, the angle is formed by rays AC and AT, which form the sides of the angle. They share endpoint A, which is the angle's vertex. Point S is an interior point because it's inside the angle, and point H is an exterior point because it's on the outside. This angle can be named 4 ways: angle A, angle CAT, angle TAC, or just angle 1. Notice that the vertex A is always listed in the middle of both the CAT and TAC notations.
Look at these 2 angles here, YAP and DOG. The measure of angle YAP is 60 degrees. We see that the measure of angle DOG is 60 degrees also. So as we said earlier, 2 angles that have equal measures are congruent. So the measure of angle YAP is equal to the measure of angle DOG, and angle YAP is congruent to angle DOG.
YAP and DOG are what we call acute angles. Acute angles measure less than 90 degrees.
A right angle measures exactly 90 degrees. We designate a right angle by putting a small square at the vertex of the angle. An obtuse angle measures more than 90, but less than 180 degrees. A straight angle measures exactly 180 degrees. Note that a straight angle looks just like a straight line. We told you geometry is mystical.
Now that we have single angles down, let's look at some pairs of angles that have special names.
First, adjacent angles. Adjacent angles are coplanar angles, you know, the kind that lie in the same plane. They have a common vertex and a common side. Since the adjacent angles are touching and not overlapping, they have no common interior points.
Next, let's look at complementary angles. Complementary angles are 2 angles whose measures add up to 90 degrees, like angles Y and O here. The measure of angle Y is 33 degrees, and the measure of angle O is 57 degrees. If we add the measures of angle Y and angle O together, we get 90 degrees, the measure of a right angle. So angles Y and O are complementary.
Supplementary angles are 2 angles whose measures add up to 180 degrees. Like angles D and A. The measure of angle D is 99 degrees, and the measure of angle A is 81 degrees. We add the measures of angle D and angle A together for a total of 180 degrees, which is the measure of a straight angle. So, angle D and angle A are supplementary.
Notice that complementary and supplementary angles do not need to be adjacent. It's all about their measures. They could be lying around just about anywhere, as long as their measures add up just right.
Next, vertical angles. Vertical angles are 2 angles that occur opposite each other when 2 lines intersect. When these 2 lines intersect, they form 4 angles. In this diagram, angles 1 and 2 are vertical angles. So are angles 3 and 4. The cool thing about vertical angles is that they're congruent. So if you know the measure of one, you also know the measure of the other.
For example, if we're given the measure of one of these angles, we could figure out the other three. Watch this. If angle 1 is 55 degrees, then angle 2 is also 55 degrees, because they're vertical angles. See that angles 1 and 3 are supplementary angles? Together, their measures will add up to 180 degrees. We know the measure of angle 1 is 55 degrees, so angle 3 measures 180 degrees minus 55 degrees, or 125 degrees. Angle 4 also measures 125 degrees because angles 3 and 4 are vertical angles. So we've got all four.
Vertical angles are really powerful tools that we'll use a lot when we get to proofs. But before we get to proofs, let's look at some other angle stuff.
An angle bisector is a ray that splits an angle smack dab in the middle, forming two congruent adjacent angles. Here, ray QR bisects angle SQT. Angle SQR is congruent to angle TQR. Note the curve symbol inside of each of the angles. If there's a slash in each one, then that means the angles are congruent.
And finally, perpendicular lines are intersecting lines that form right angles. Rays and segments can also be perpendicular. Here we have two perpendicular lines, L and M. So all four angles, D, O, G, and S, are right angles. When we write that two lines are perpendicular, we use a special symbol. L is perpendicular to M.
Now that we know all about angles and their special names, it's time to get theorem-y about angles.
Section B, angles and their theorems.
Before we get into angles and their theorems, we need to review some algebraic properties that we'll be using in a few minutes. These are really useful because these properties work for equal and congruent statements.
Let's start with the reflexive property. The reflexive property states that a value is equal to itself. You know, like when you look into a mirror and you see your own reflection.
In geometry, we'll use the reflexive property to state that an angle or segment is congruent to itself. This may sound kind of obvious, but it'll actually come in very handy in geometry. You'll see.
We'll also be using the substitution property. Let's say we have two statements. The measure of angle 1 plus the measure of angle 3 equals 180. And the measure of angle 1 is equal to the measure of angle 2. By using the substitution property, we can switch two values that are equal, the measure of angle 1 and the measure of angle 2 in our first statement. So, the measure of angle 2 plus the measure of angle 3 equals 180. Switching the values of the measure of angle 1 and the measure of angle 2 is substitution.
All right, now let's look at the transitive property, which says that if A equals B and B equals C, then A equals C.
Here's an example of the transitive property. Say that you get the same haircut as your friend, and your friend has the same haircut as the monkey. Then according to the transitive property, you have the same haircut as the monkey. But don't worry, it looks good on you.
Now that we've got those properties of algebra under control, we're going to get into the angle-related theorems. These are important theorems we'll be using in later proofs, so be sure to go back and review this section to make sure you get them down.
Theorem. If two angles are the complements of two congruent angles, then the two angles are congruent.
You see how that works? If angle 1 and angle 2 are the complements of angle 3 and angle 4, and angle 3 and angle 4 are both 60 degrees, then angle 1 and angle 2 must be 30 degrees. So they're congruent. This works the same way with supplementary angles. Here's that theorem.
Theorem. If two angles are the supplements of two congruent angles, then the two angles are congruent.
Now here's the theorem about angle bisectors.
Theorem. Every angle has exactly one bisector. Remember how we said that each segment has exactly one midpoint? Well, the same is true of angle bisectors. So as angle CUT is bisected by ray UP, we get two congruent angles, CUP and TUP.
When do we get to prove a theorem?
Real soon.
Now, I am tired of this inactivity, okay? I got cabin fever, all right? I'm young, I'm alive.
Okay, we'll do a proof. But first, there's some things you need to know. A proof is just a series of logical steps that prove the truth of a theorem. Before we prove anything, we're given some information. We'll use this given information to set up our theorem, which in this case proves a property of vertical angles we're already familiar with.
Our theorem says that two vertical angles are congruent to one another. So, given that angle 1 and angle 2 are vertical angles, we'll prove that angle 1 and angle 2 are congruent. And in a broader sense, we'll prove that two vertical angles are congruent.
One more thing. As we go through the process of proving theorems, we'll set up a proof table. We'll put statements on the left and reasons on the right. You may not understand why we do each step right now, but don't worry, it'll all make sense in the end.
Here we go. We'll begin by stating our given information. Angle 1 and angle 2 are vertical angles. No big whoop. Our second statement is the sum of the measures of angle 1 and angle 3 equals 180. And the sum of the measures of angle 2 and angle 3 equals 180. How do we know this? Because angle 1 and angle 3 form a straight angle, which measures 180 degrees. Ditto for angle 2 and angle 3. Our reason, this is the definition of a straight angle.
Next, we'll set the sum of the measures of angle 1 and angle 3 equal to the sum of the measures of angle 2 and angle 3. Our reason is the substitution property, because, as we saw in step 2, each side of the equation equals 180.
Our fourth step is setting the measure of angle 3 equal to the measure of angle 3. Our reason? It's the good old reflexive property.
Now that we've established that the measure of angle 3 is equal to itself, our next step is to subtract the measure of angle 3 from each side. Our reason here is just plain old everyday algebra. Once we do that, we're left with the measure of angle 1 equals the measure of angle 2. And because of the definition of congruent angles, we know angle 1 is congruent to angle 2. So we've proved the theorem that says vertical angles are congruent.
We all enjoy proving theorems. Now, don't forget all the tools that you have at your disposal when doing proofs. There's given information, definitions, postulates, algebra, algebraic properties, and previously proven theorems.
Proofs are an excellent example of both inductive and deductive reasoning. Setting a goal for a proof is an inductive process, and because we support each step by reason, we're thinking deductively. So, our little brains are really working. We'll look at some more proofs in a few minutes, but for now, it's time for a little look back.
An angle is formed by two rays that share an endpoint. Adjacent angles are coplanar angles that share a common vertex and side. Complementary angles are two angles whose measures add up to 90 degrees. Supplementary angles are two angles whose measures add up to 180 degrees.
Vertical angles are congruent. An angle bisector is a ray that splits an angle smack dab in the middle. Perpendicular lines are two lines that form right angles where they intersect. And a proof is a series of logical steps that prove the truth of a theorem.
Section C, parallel lines and angles.
As we discussed earlier, parallel lines are two or more lines that are contained in a plane and never touch.
The parallel postulate is one of the most important postulates in geometry. It says, given a line, L, and a point, P, not on that line, there's exactly one line, M, through the point P that is parallel to line L.
Did you get that? So I've got a line and I've got a point, all in the same plane. The parallel postulate says that there's only one line going through the point that's also parallel to the line.
Although an infinite number of lines could go through point P, only one runs parallel to line L. This is what all of Euclidean geometry is based on. Now that we're familiar with the parallel postulate, we can discuss some special facts about parallel and not parallel lines and the angles formed when an intersecting line comes to town.
When two lines are cut by a line, we call this intersecting line a transversal. When the lines are cut by the transversal, 8 different angles are formed. See them all there? There are 4 different ways to categorize these angles. The most general way is corresponding angles. Angles 1 and 5, 2 and 6, 3 and 7, and 4 and 8 are corresponding angles because they're in the same position on either line. They correspond to each other.
Angles 3 and 5 and 4 and 6 are alternate interior angles. They're all interior angles because they're between the two lines. The pairs we mentioned are alternate interior angles because they are on alternate or opposite sides of the transversal.
Angles 1 and 7 and angles 2 and 8 are alternate exterior angles. These guys are all exterior angles because they are on the outside of the lines. Again, the pairs are alternate exterior angles because they are on opposite sides of the transversal.
Angles 3 and 6 and 4 and 5 are same-side interior angles because, well, the pairs are all interior angles on the same side of the transversal.
Now that's a lot of angles for just 2 lines and a transversal, but it's not too tough. Now let's change the situation a little. We have the transversal intersecting a pair of parallel lines. Let's check out the corresponding angles.
What if we measure the corresponding angles in this diagram? Look specifically at angles 1 and 5. They seem to be congruent, right? What about angles 3 and 7? They seem to be congruent as well. So using inductive reasoning, we'll assume the following 2 statements in the form of if P then Q. Our first statement is, if 2 parallel lines are cut by a transversal, then the corresponding angles are congruent. And in the form of if Q then P, our second statement is, if 2 lines are cut by a transversal and the corresponding angles are congruent, then the 2 lines are parallel.
We'll use our deductions here to form a double fact statement that can be summarized as the corresponding angle postulate. Lines are parallel if and only if corresponding angles are congruent. We'll accept this as a postulate because we don't have enough information in our earlier postulates and theorems to prove it yet.
So what we've done is we've used inductive reasoning to develop the corresponding angle postulate. Once we accept this postulate, we can prove theorems about alternate interior angles and about alternate exterior angles.
I accept it.
Okay, great. Let's look at alternate interior angles. The theorem we want to prove is lines are parallel if and only if alternate interior angles are congruent. We need to prove each statement separately because this, like the corresponding angle postulate, is really 2 statements in one. The first statement, the if P then Q part, is if a transversal cuts 2 parallel lines, then the alternate interior angles are congruent. The second statement, if Q then P, is if a transversal that cuts 2 lines creates congruent alternate interior angles, then the lines are parallel. Let's do a proof.
We'll start with the first statement we just identified and prove that, then move on to the second statement. The first statement was, if a transversal cuts 2 parallel lines, then the alternate interior angles are congruent. So given that the lines L and M are parallel, we'll prove that angle 3 is congruent to angle 5. Okay, let's set up our proof table. First, we state our given information. Line L is parallel to line M.
For our second step, we state that angle 1 and angle 5 are congruent. We do this because of the corresponding angle postulate we just talked about. Remember the corresponding angle postulate? It says that corresponding angles, like angles 1 and 5, are congruent.
In our third step, we state angle 1 is congruent to angle 3. The reason we do this is because of the theorem we proved earlier. Vertical angles are congruent, which says, well, that vertical angles, like angles 1 and 3, are congruent.
Our final statement is angle 3 is congruent to angle 5. We can say this because of the transitive property.
In our theorem, we've shown that angle 1 is congruent to both angle 5 and angle 3. Because of this, we can use the transitive property as our reason to say that angles 3 and 5 are congruent to one another. And since angle 5 and angle 3 are congruent alternate interior angles, we've proven our goal. Alternate interior angles are congruent.
Before we go on to the second part of our theorem, notice that we'll be proving the converse of the statement we just proved. And notice that as we prove this second part, we'll apply much of the same reasoning we just used.
So we're going to prove the converse of the alternate angles are congruent theorem, which states the transversal that cuts 2 lines creates congruent alternate interior angles, then the lines are parallel. To prove our theorem, we're given that angle 3 is congruent to angle 5. We need to prove that lines L and M are parallel.
Let's set up our proof table. Our first step is to state our given information. Angle 3 is congruent to angle 5.
Next, we state that angle 3 is congruent to angle 1. We can do this because angle 3 and angle 1 are vertical angles, and vertical angles are congruent.
Our third statement is angle 1 is congruent to angle 5. This is true because we're applying the transitive property to angle measures.
Notice that we could not have entered corresponding angle postulate as our reason in step number 3. At this stage of the proof, we hadn't proven that corresponding angles are congruent. We do not yet know if the lines are parallel. This is what we're trying to prove. So, be careful with the postulates you start throwing around. That's it.
However, now we know that the corresponding angles are congruent, so it's time to use the corresponding angle postulate. Line L is parallel to line M because of the corresponding angle postulate. And we're done.
So, we've proven each half of the alternate interior angles theorem. Now we can yell from the mountaintops that lines are parallel if and only if alternate interior angles are congruent.
Moving right along, the alternate exterior angle theorem states that lines are parallel if and only if alternate exterior angles are congruent. We won't prove the alternate exterior angle theorem because it's so similar to the alternate interior theorem, and we wouldn't want to cover this same old territory again. So let's check out the same side interior angle theorem. It's different. How different? Let's take a look.
Remember what same side interior angles are? They're these guys right here. Looking at the diagram, we can see that these angles aren't congruent. It looks like the supplementary, doesn't it? We'll test our observation by proving this theorem. Two lines cut by a transversal are parallel if and only if same side interior angles are supplementary. Like the if and only if statement we just proved, we know that this is really two statements in one. The first statement, the if P then Q part, is if a transversal cuts two parallel lines, then the same side interior angles are supplementary. Let's go ahead and prove this theorem. We'll get to the second part in a minute.
Given that line L is parallel to line M, we want to prove that angles 4 and 5 are supplementary. Okay, let's set up our proof table. Our first step is to state our given information. L is parallel to M.
Next, we state that angle 1 is congruent to angle 5. Our reason is the corresponding angles postulate.
Step 3 is the sum of the measures of angle 1 and angle 4 equals 180. We know this because of the definition of a straight angle.
Step 4. Because angle 1 is congruent to angle 5, we use substitution as our reason for stating that the measure of angle 4 plus the measure of angle 5 equals 180.
Step 5. Two angles whose measures total 180 degrees form supplementary angles, and so angle 4 and angle 5 are supplementary angles. We've proved what we set out to.
So, we've proven half of our proof. Remember, we're proving an if and only if statement, so we must proceed both forward and backward. So, the second statement of the proof is the reverse or the converse of the first.
In the form of if Q then P, our converse statement is if a transversal that cuts two lines creates supplementary same-side interior angles, then the lines are parallel. So, given that angle 4 and angle 5 are supplementary, we'll prove that L is parallel to M.
Our first statement is our given information. Angle 4 and angle 5 are supplementary.
Our second statement is the sum of the measures of angle 4 and angle 5 equals 180 because of the definition of supplementary angles.
Next, we'll state that the sum of the measures of angle 4 and angle 1 equals 180. This is the definition of a straight angle.
In our fourth step, because the equations in step 2 and 3 equal 180, we can set the two equations equal to one another. The sum of the measures of angle 4 and angle 5 equals the sum of the measures of angle 4 and angle 1. This is possible because of the substitution property.
Next, we can drop like terms, the measure of angle 4, on both sides of the equation. Thanks to algebra, this leaves us with the measure of angle 5 equals the measure of angle 1. This also means that angle 5 is congruent to angle 1 because of the definition of congruence.
Our final statement is L is parallel to M. How can we say this? Well, now that we've got angle 5 congruent to angle 1, we can use the corresponding angles postulate.
So, we've proven the same side interior angles theorem. Lines are parallel if and only if same side interior angles are supplementary. Now, we've made it to the end of the section. Want to take a look back?
You got it. The parallel postulate is one of the more important postulates. It says that for any line L and point P not on line L, there's exactly one line M through point P that runs parallel to line L.
When a transversal cuts two lines, 8 angles are formed. We categorize them as corresponding angles, alternate interior angles, alternate exterior angles, and same-side interior angles.
The corresponding angle postulate says that lines cut by a transversal are parallel if and only if corresponding angles are congruent. The alternate interior angles theorem states that lines cut by a transversal are parallel if and only if alternate interior angles are congruent.
Likewise, the alternate exterior angles theorem states that lines cut by a transversal are parallel if and only if alternate exterior angles are congruent. The same-side interior angle theorem says that lines cut by a transversal are parallel if and only if same-side interior angles are supplementary. That's it.
Quiz 2.
Part 3. World of Triangles.
Section A, Definitions and Basic Facts.
Welcome to the world of triangles. A triangle is a figure formed by 3 segments joining 3 non-collinear points, which means it's a 3-sided shape. Everyone knows that. These 3 segments are called the triangle sides. Each side meets another at a vertex where they form an angle.
There are 2 ways to classify triangles, either by the lengths of their sides or by their angles.
First, by side length, we have equilateral triangles, which have 3 congruent sides, like triangle A here. All sides measure 4 inches.
There are also isosceles triangles, which have 2 congruent sides. Triangle B has 2 sides that equal 4 inches. We call the other side the base. The base can be on any side. Like, if we turn triangle B on its side, or upside down, its base is still 2 inches.
Triangle C is scalene, which means it has no congruent sides. It's just a mess. It's all over the place.
So those are the 3 ways to describe triangles by the length of their sides. There are 4 other ways to classify them by angles. Let's take a look.
Equiangular triangles have all 3 angles congruent. In triangle D here, each angle measures 60 degrees. We'll see that all equiangular angles measure 60 degrees. Plus, notice that this is also an equilateral triangle. All equiangular triangles are equilateral, and vice versa.
Right triangles have 1 right angle. Other parts of right triangle E here are its 2 legs, which form the right angle, and the side opposite the right angle is called the hypotenuse. We'll talk more about right triangles later.
Obtuse triangles have 1 obtuse angle. So triangle F here has angles that measure 30 degrees, 35 degrees, and the obtuse angle, which is 115 degrees.
Acute triangles have 3 acute angles. Triangle G has triangle measures of 40, 60, and 80 degrees.
So now we know how to classify triangles, both by their sides and their angles. We can also classify triangles by their elements: earth triangle, fire triangle, air triangle, and water triangle. Get it? Elements: earth, air, fire, water. Now let's prove an important theorem about triangles that says the sum of the angular measures of a triangle is 180 degrees.
Remember that we haven't proven anything at all about triangles yet. The only things we know are they have 3 sides and 3 angles. Using inductive reasoning, we think that the measures of the angles of all triangles add up to 180 degrees. Using deductive reasoning, we're going to have to use what we already know about geometry to prove this.
Our theorem is the sum of the measures of the angles in a triangle is 180 degrees. Given that ABC is a triangle, Prove that the sum of the measures of angle 1, angle 2, and angle 3 equals 180 degrees.
Now, for the first step of our proof, we state our given information. ABC is a triangle. For our second step, we got to do a little trick. We need to add a line to the diagram to help us prove our point. This is okay because we're not changing our triangle. The line we're adding runs parallel to segment BC. With this line, we'll be able to use the parallel line theorems we just proved, involving the relations of their angles. So, step 2 is we draw a line through A parallel to BC. We do this because of the parallel postulate.
Remember the parallel postulate? This is what all of Euclidean geometry is based on. It says that, given a line L and a point P not on the line, there is exactly one line M through P that's parallel to L. Lines L and M are therefore parallel.
Our next statement is, the sum of the measures of angle 4, angle 2, and angle 5 equals 180. This is the definition of a straight angle. Don't be confused by the 3 angles here. In this diagram, we have 3 angles that make up the straight angle. Now let's go on to our next step.
Remember the alternate interior angles theorem? Lines are parallel if and only if alternate interior angles are congruent. The alternate interior angles theorem allows us to state that angle 4 is congruent to angle 1, and angle 5 is congruent to angle 3. Good deal.
Finally, because of substitution, we can state our goal. The sum of the measures of angle 1, angle 2, and angle 3 equals 180. You see how we substituted the information in our last step into the information in the step before it to get this answer? That's some snazzy proofing for you, and we're done.
So, why did we go through the trouble of proving that the angular measures of a triangle add up to 180 degrees? Well, the following statements can be proven based on the proof we just gave. These are called corollaries of the theorem. A corollary is an extra bit of information that can be proven along with the proof of our theorem. We want to know them because they can be used as reasons to prove other theorems. Let's take a look at them.
Our first corollary is, if 2 angles of one triangle are congruent to 2 angles of another triangle, the third angles are also congruent.
Isn't that amazing?
Our second corollary is, a triangle can have only one obtuse angle. If we have more than 90 of the 180 degrees accounted for by an obtuse angle, we have less than 90 degrees left for our other 2 angles, neither of which can be obtuse.
How amazing is that?
Our next corollary is a triangle can have only one right angle. If we have 90 of the 180 degrees accounted for by a right angle, we have exactly 90 degrees for our other 2 angles. So, the others could be 45 and 45 degrees, 60 and 30 degrees, or even 89 and 1 degrees. But there can only be one right angle.
Welcome to Planet Amazing.
Our last corollary is, the acute angles of a right triangle are complementary. So what this is saying is, by definition, we have 90 of the triangle's 180 degrees accounted for by the right angle, and we have 90 degrees remaining for the other 2 angles. The definition of complementary angles is 2 angles whose measures add up to 90 degrees.
Alex, I'll take amazing for 1,000.
So there we have it. We'll use these corollaries later on as we work more with triangles. In fact, let's use some of them now.
In this diagram, the exterior angle, angle 4, and angle 1 are supplementary. They form a straight angle. Therefore, the sum of the measures of angle 4 and angle 1 equals 180 degrees. Just like the sum of the measures of the angles of a triangle is also 180 degrees. Let's prove that the measure of angle 4 is equal to the sum of the measures of the 2 remote interior angles.
Remote interior angles? What the?
Oh yeah. Remote interior angles are the 2 interior angles, angles 2 and 3, which are not adjacent to the exterior angle, angle 4. You see? They're remote.
So, the theorem we're trying to prove is, the measure of an exterior angle is equal to the sum of the measures of the 2 remote interior angles. To prove that the measure of angle 4 equals the sum of the measures of angle 2 and angle 3, we're given the information that triangle ABC has exterior angle 4.
Let's set up a proof table. Our first statement is our given information. Triangle ABC has exterior angle 4. Second, we state that the sum of the measures of angle 1, angle 2, and angle 3 is 180 degrees. Our reason is this. The measures of the interior angles of a triangle add up to 180.
Our third statement is the sum of the measures of angle 1 and angle 4 equals 180 degrees. This is the definition of a straight angle.
Because the left-hand sides of the equations in steps 2 and 3 equal 180 degrees, we can combine them using substitution as our reason.
Algebra allows us to drop the measure of angle 1 on each side, leaving us with our goal. The sum of the measures of angle 2 and angle 3 equal the measure of angle 4. So we've proved that the sum of the remote interior angles is equal to the measure of the exterior angle.
All right, now that we know how to measure the angles of triangles, we're going to use this information to prove that two triangles are congruent.
Section B, proving triangles congruent.
What do we mean by congruent triangles? Well, we say that two triangles are congruent if and only if their corresponding parts are congruent. This is a very powerful statement. Let's see what it means.
Here are two congruent triangles. To precisely state their congruence, we say triangle ABC is congruent to triangle DEF. We can't say triangle ABC is congruent to triangle FED. Why? Well, let's see why.
By saying that triangle ABC is congruent to triangle DEF, we're saying that corresponding angles and sides are congruent. So, angle A is congruent to angle D. Angle B is congruent to angle E. Angle C is congruent to angle F. Segment AB is congruent to segment DE. Segment BC is congruent to segment EF. And segment AC is congruent to segment DF. If we were to say that triangle ABC is congruent to triangle FED, we'd also be saying that angle A is congruent to angle F, which is wrong. Notice how we show what parts are congruent in the diagram? We mark them with little lines to show which ones match up.
Note that the definition, two triangles are congruent if and only if their corresponding parts are congruent, uses the phrase if and only if, reminding us that this statement is really two statements, the statement itself and its converse.
Our statement is, if two triangles are congruent, all of their corresponding parts are congruent. This statement will be very useful to us later on when we work out more proofs. In fact, we'll refer to this definition so much it's often given nicknames like the definition of congruence, fuzzy face, and CPCTC, which stands for corresponding parts of congruent triangles are congruent.
The converse is, if two triangles have congruent corresponding parts, then the two triangles are congruent. Because this statement requires us to find 6 matching pairs of items, all 3 pairs of sides, and all 3 pairs of angles, before we can claim that two triangles are congruent, it takes a lot more time than our first statement. We don't really need all of that stuff to prove that two triangles are congruent. Just wait, you'll see.
So let's do a few experiments to try to come up with 3 different postulates to use in our triangle proofs.
First, try this. Put your fingertips together like this. Now, bend the middle fingers together so the first knuckles are touching. Now, try to take your ring fingers apart without moving your other fingers. You won't be able to.
Try this. Take 2 drinking straws. Cut the first one into 3 pieces, one 4 inches, one 3 inches, one 2 inches. Do the same with the second straw so that you have 2 identical sets of 3 pieces. Make a triangle out of each set. Try to make the triangles look different. You won't be able to. If 2 triangles have the same side lengths, they will always be the exact same shape.
This is a key postulate in geometry, the side-side-side, or SSS postulate. So we don't need to match all 6 pairs of sides and angles. It's enough to just match the 3 sides to prove that the two triangles are congruent.
Side, side, side postulate.
Side, side, side postulate. If 3 sides of one triangle are congruent to 3 sides of another triangle, then the triangles are congruent. The side, side, side postulate.
Let's try an example where we can put the side-side-side postulate to good use. This isn't a theorem we're proving, just a specific problem that you might find on a test. We'll use a proof table to work it out.
Given triangle QRS, with M as the midpoint of RS and QR congruent to QS, prove that triangle QRM is congruent to triangle QSM.
Note that we are not given the information that QM is the bisector of angle Q.
Let's set up our proof table. Our first step is to put down all of our given information. M is the midpoint of RS, and segments QR and QS are congruent.
Our second step is to state that segments RM and MS are congruent. That's the definition of a midpoint.
So, now we've got two pairs of sides congruent. The pair we're given, QR and QS, and the two that are divided by the midpoint, RM and MS. The only side left is QM, which is easy to prove. Because it's shared by both triangles, we just state that QM is congruent to itself by using the reflexive property.
Now that we've got all three sides congruent, we can state our goal. Triangle QRM is congruent to triangle QSM, thanks to the side, side, side postulate.
Pretty simple, huh? We've just used the side, side, side postulate to prove that two triangles are congruent. Now, let's take a look at the side, angle, side postulate.
We'll start with another experiment. Get a friend, 2 rulers, 2 protractors, 2 sheets of paper, a baseball, a glove, and a bat.
Pick 2 side lengths and 1 angle measure. Let's say the sides measure 4 inches and 7 inches, and the angle is 82 degrees. Now both of you draw triangles which have a 4-inch side, a 7-inch side, and an angle of 82 degrees between them. Your triangles should look the same. This illustrates another important postulate of geometry, the side angle side or SAS postulate. Good job. Now go play baseball.
The side angle side postulate.
The side angle side postulate. If two sides and the included angle of one triangle are congruent to two sides and the included angle of another triangle, then the triangles are congruent. The side angle side postulate.
Here we have two triangles that resemble the last pair. In fact, they went to high school together and ran in the same social circles. We'll use the side angle side postulate to prove they're congruent. What we need to do is prove that they have two congruent corresponding sides and one congruent angle in between. Given that AB is congruent to BC and BD is congruent to BE, we'll show that triangles BAD and BCE are congruent.
Let's get started by stating our given information. Segment AB is congruent to segment BC, and segment BD is congruent to segment BE.
So, we have been given two pairs of sides. To use the side angle side postulate, all we need to prove is that the angles between the sides, angle 1 and angle 2, are congruent. And we notice that angle 1 and angle 2 are vertical angles. Remember the definition of vertical angles? Vertical angles occur opposite each other when two lines intersect, and vertical angles are congruent. So, we can state that angle 1 is congruent to angle 2, because of the definition of vertical angles.
So, for triangles BAD and BCE, we have two sides and their included angles. We complete our proof by stating that triangle BAD is congruent to triangle BCE. Our reason is the side angle side, or SAS postulate. We're done!
Let's try one last experiment. With a friend of yours, agree on 2 angle measurements. Remember, they can't both be 90 degrees or greater, and 1 side length. Now draw a triangle starting with an agreed-upon side length and putting the agreed-upon angles at each end of the side. Say that you start with a 36-inch side. Put a 40-degree angle on one end and a 60-degree angle on the other. Now complete the triangles. Once again, your triangles should look identical. We have illustrated the following important postulate of geometry, the angle side angle, or ASA postulate.
Angle side angle postulate.
Angle side angle postulate. If two angles and the included side of one triangle are congruent to two corresponding angles and the included side of another triangle, then the triangles are congruent. The angle side angle postulate.
Let's look at the triangles here, ABC and EDC. Let's prove them congruent. Sound good? Great. Let's state our given information. We're given that AB and DE are parallel to one another and their lengths are congruent. We want to prove the triangles are congruent using the angle side angle postulate.
Let's get started by stating our given information. Lines AB and DE are parallel, and AB and DE are congruent.
Remember the alternate interior angles theorem? Lines are parallel if and only if alternate interior angles are congruent. Well, we'll use it for our reason in step 2. It lets us state that angles A and E and angles B and D are congruent to each other.
So, for each triangle we have a corresponding side, and two angles at its ends. By using the angle-side-angle postulate, we can set triangle ABC congruent to triangle EDC. Our goal is accomplished.
Now that we have some ways to prove congruent triangles, let's move on to using congruent triangles.
Section C, using congruent triangles.
In the last section, we learned how to use three postulates that prove two triangles congruent. In this section, we'll also want to conclude that a particular pair of angles or segments are also congruent. We can do this because of CP-CTC, or corresponding parts of congruent triangles are congruent. Let's start with a parallelogram, which is a four-sided polygon that has two pairs of parallel congruent sides.
Here we have parallelogram ABCD, which is cut by segment BD, making two triangles, BAD and DCB. We're given that segment AB is congruent to segment CD, and segment AD is congruent to segment BC. And we want to prove that angles 1 and 2 are congruent.
Do you see how we'll do this? We'll prove the triangles are congruent to one another. Then we'll use CP-CTC to prove that corresponding angles 1 and 2 are congruent.
Let's start by stating our given information. AB is congruent to CD, and AD is congruent to BC. We have two pairs of corresponding sides, and we can get the third pair easily. With the reflexive property, we can state that the side shared by both triangles, BD, is congruent to itself. Now we have three corresponding sides.
With these three pairs of congruent corresponding sides, we can use the side-side-side postulate to conclude that triangles ABD and CDB are congruent. Because angles 1 and 2 correspond, our last step is to state that they're congruent because of CP-CTC. Corresponding parts of congruent triangles are congruent.
So, our good friend CP-CTC is pretty helpful once we establish that two triangles are congruent, because then there are all kinds of things we can establish as congruent. Sometimes we can even determine that a pair of lines are parallel by the CP-CTC method. Think about it. If we prove congruent triangles, then we've also proven congruent angles. If these angles happen to be corresponding or alternate interior angles, then the lines must be parallel. Make sense? Let's prove it.
Here's our pair of triangles. Given that LN is congruent to NQ and MN is congruent to NP, we'll prove that LM is parallel to PQ.
First, we'll state our given information. LN is congruent to NQ, and MN is congruent to NP.
Second, we know that angle 1 is congruent to angle 2 because vertical angles are congruent.
Now we have two pairs of sides and a pair of angles established as congruent. So we can say that triangle LMN is congruent to triangle QPN because of the side-angle-side postulate. We've got congruent triangles.
Because we have congruent triangles, we know angle 3 is congruent to angle 4 because of our good friend CP-CTC.
Finally, because angle 3 and angle 4 are alternate interior angles, we can state that LM is parallel to PQ. The reason is the alternate interior angles theorem, and we've proven our point.
Now, let's take a look at isosceles and right triangles.
Section D, isosceles and right triangle theorems.
So now that we have a good footing in the world of triangles, let's look at a couple of special types of triangles, the isosceles triangle and the right triangle.
We'll begin with the isosceles triangle. Remember isosceles triangle basics? An isosceles triangle is a triangle with two congruent sides. These two sides are called the legs. The third side is called the base. The angles formed by the base and legs are called the base angles, and the third angle is called the vertex angle.
Let's do a proof.
Given that sides AB and AC are congruent, prove that base angles B and C of isosceles triangle ABC are congruent.
First, we'll get started by stating our given information. Sides AB and AC are congruent.
Second, we'll draw AD, the bisector of angle A.
Why do we do this? We need a way to use one of our newly learned triangle postulates, side, 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 angle, side, angle, or side, angle, side. Our reason is every angle has exactly one bisector.
The definition of an angle bisector, allows us to state that angle DAB is congruent to angle DAC.
We can prove that side AD is congruent to side AD because of the reflexive property. Boy, that reflexive property sure is great.
We have two pairs of sides and the pair of included angles. So triangle ABD is congruent to ACD because of the side-angle-side postulate.
Now we can state our goal. Angle B is congruent to angle C because corresponding parts of congruent triangles are congruent, or CP-CTC. Done.
So we've proven that the base angles of an isosceles triangle are congruent. Let's try another theorem that'll prove that the legs opposite those congruent angles are also congruent.
We're given that angles B and C are congruent, and we want to prove that legs AB and AC are congruent in isosceles triangle ABC. Let's get started.
First, we'll state our given information. Angle B is congruent to angle C.
Next, we draw AD, the bisector of angle A, because every angle has exactly one bisector. I'm telling you, this is the key. Now, we've got two triangles to work with, and we're in business.
By the definition of an angle bisector, we know that angles BAD and CAD are congruent.
So far, this proof is really similar to the one we just did, which is fine, but we're going to change it up now.
Because we've just established that the two angles at the top are congruent and angles B and C are congruent, we know the third pair of angles must be congruent too. Our fourth step is to state the congruence of angles ADB and ADC. This is because the sum of angular measures is 180.
We want to use the angle side angle postulate. We have all the angles we'll need. Now we just need a side length.
To give us a congruent pair of sides, we state AD is congruent to AD. This is because of the reflexive property. There it is again, real handy.
Now we can state that triangle ABD is congruent to triangle ACD because of the angle side angle postulate.
Finally, we can say that AB is congruent to AC because corresponding parts of congruent triangles are congruent, or CP-CTC, and we've proven our theorem.
Nice job! In addition to our three postulates, there's a theorem we can use to prove triangles congruent. You may have noticed in our last example that having two pairs of angles and one pair of non-included sides congruent is good enough to prove congruent triangles. So here's our new theorem.
The angle-angle-side theorem says that if two angles and a non-included side of a triangle are congruent to the two corresponding angles and non-included side of another triangle, then the two triangles are congruent.
Angle-angle-side is a good theorem to remember, but you won't use it as often as the side-side-side, angle-side-angle, or side-angle-side postulates, so we won't take the time to prove it. Just keep it in your back pocket for later.
Just like a free lunch or a peace treaty called NITO, there's no such thing as a side-side angle theorem. Here's why. This is an example of two triangles with congruent pairs of sides and a congruent pair of non-included angles. But the triangles are certainly not congruent. They're not even in the same ballpark.
For right triangles, there's a special theorem we can use to prove them congruent. It's called the hypotenuse leg, or HL theorem. Take a look.
To describe the hypotenuse leg theorem, we need to review a couple of terms related to right triangles. First, the two sides which form the right angle are called the legs. The side opposite a right angle and the longest side of a right triangle is called the hypotenuse. So, the hypotenuse leg, or HL theorem, states that if the hypotenuse and leg of one right triangle are congruent to the hypotenuse and a leg of another right triangle, then the two right triangles are congruent.
So let's consider the hypotenuse leg theorem with right triangles TUB and HOP here. We know that their hypotenuses are both 5 inches, and they each have a leg that is 3 inches. So, because they're right triangles, they're congruent because of the hypotenuse leg theorem.
There are 3 ways to describe triangles by their sides. Equilateral, with 3 congruent sides, isosceles, with 2 congruent sides, and scalene, with no congruent sides. We have 4 ways to describe triangles by their angles. If they have 3 congruent angles, they're equiangular. If they have 3 acute angles, they're acute triangles. If they have 1 right angle, they're right triangles. If they have 1 obtuse angle, they're obtuse triangles.
Corresponding parts of congruent triangles are congruent. This is also known as CPC-TC. We can also prove the congruence of triangles with the side-side-side postulate, the side-angle-side postulate, and the angle-side-angle postulate.
The angle-angle-side theorem says that if we know 2 angles and a non-included side of 2 triangles are congruent, then the 2 triangles are congruent. With right triangles, we can use the hypotenuse leg theorem.
Quiz 3.
Can't operate. Play.
Well, that's it for Quiz 3. And that's it for the Many-Sided World of Geometry, Part 1. We've covered points, lines, rays, angles, postulates, theorems, proofs, parallel lines, transversals, and even the congruence of triangles. If you've gotten this far, then you're ready to tackle the Proof-O-Rama, our proof-based final exam. You can get there from the main menu. And give us a call at 1-800-238-9669 if you have any questions or comments about this program. Let us know what's on your mind. We'd love to hear from you. Bye-bye.
To continue your mathematical brain expansion, check out these other programs from the award-winning Standard Deviance series: Geometry Part 2, Trigonometry, Pre-Calculus, and Calculus. They're like jumper cables for your brain.